I'm going to look at cosets. And I'm going to say that if you have two different cosets, or two cosets, maybe I'll even rephrase that, two names for cosets here, either they're going to be equal or they are going to have nothing in common at all. And what this is going to mean is if you have a group G, that means that you can partition, right, here's G, you can partition that into just cosets where there's no overlap. So here might be G, H of A, H of B, H of C, H of D, H of E, and H of F. And I'm saying that every element of G will be in exactly one of the cosets. Exactly one. There's no overlap between them. So what do we mean by this? Let's take a look at this subgroup. Let's take a look at the cosets. Well, there are three different cosets. Those two are equal, those two are equal, those two are equal. And notice either if A is E and B is 1, 2, they might be exactly the same. Or if H is 1, 3 and H is 1, 2, 3, so if A is equal to 1, 3 and B is equal to 1, 2, 3, you might get exactly the same set. But otherwise, if that's not to happen, if they're not exactly the same, then they have nothing in common. Look at these two. 1, 3 is in this, but it's not in there, and it's not in there. 1, 2, 3 is in there, but it's not in there, it's not in there. There's zero overlap. That's what this theorem is saying. Either you have the exact same subset, they're the exact same coset, or they have nothing in common. So there are two cases. Either they don't intersect at all, in which case we're done, because that's one of the two good options. So let's assume that they do have section. And let's call it a C. Three different ways. So C is in both of these, because that's what it means to be in the intersection. That since C is in HA is equal to HC. We've seen that before in a previous video. Similarly, HB is C. But now we have this equality and we end up being done. So that's it. Thank you.